Now we'd actually started solving this quadratic equation using the quadratic formula in the last video, so we're going to finish that up real fast because it leads us up into complex numbers, which we'll look at in a moment. So first we had a quadratic equation in standard form, and we identified what its a, b, and c values are. Those are here. The number next to the x term is 3, the square term is 3, the linear term is 10, and the non-algebraic term is 30. We plugged those into the quadratic formula, which we derived in the last video. By using that, we can determine the roots of the parabola. That is, y is equal to 3x squared plus 10x plus 30. So we'll find those x-intercepts. After substituting everything into it, we simplified it to this, and that's kind of where I ran out of time in the video. These videos will go no longer than 15 minutes. They will cover everything that needs to be covered, but in this case, it was important to bring all this stuff back. So that brings us to a negative radical, which is where our new lesson kind of begins. What are negative radical numbers? We know that a calculator tells us that they don't work, but we're going to look at how we've managed to use them in mathematics. So if we were to factor negative 260, the largest perfect square that goes into that is 4. The remaining factor would be 65, and that would leave us over with a negative 1. Now, that square root of negative 1 is known as I, the imaginary number. Alright, and we'll see where that comes into play later. So, by simplifying this, the radical 4, that's this, becomes 2. The 65 cannot escape the radical because it is not a perfect square and has no perfect square factors. It's the product of 5 and 13, which are both prime. The square root of negative 1 will become I. And I has no real purpose on this problem at the moment. We'll explain what it's for shortly. 10 and 6 have a common factor of 3. Of 2, and so does 2 and 6. So we can simplify that to be negative 5 plus radical 65I over 3. And the other root should be negative 5 minus radical 65I over 3. Alright? And that would tell us that the roots of this parabola should be located at some imaginary locations, because if you look at the graph of y equals x squared plus 10x plus 30, it never crosses the x-axis, and that's where imaginary numbers occur. They occur when using the quadratic formula or trying to determine the roots of parabolas which have no x-intercepts. Alright, and that all brings us back to where we are now, which is discussing what this is, why this is important. Alright, so I is the imaginary number radical negative 1. Alright? Alright, so I is the square root of negative 1. If you plug it into a calculator, it will not work. Here, I'll demonstrate in my computer calculator. If we plug in 1, make that negative, and choose to take its square root, so I'm going to raise it to a power of 0.5, which, if you remember, is the same thing as taking the square root. It will tell us it can't do that. Alright? And that's because it's part of a family member of the complex numbers, which we'll take a look at right now. So the numbers we looked at before originally were counting numbers. So that's 1, 2, 3, and so on. Counting numbers were part of whole numbers, which included 0, 1, 2, 3, and so on. Those are part of rational numbers, integers, which include negative numbers as well, so negative 1, negative 0, 1, 2, and so on. Then we have, we have rational numbers, which include negative numbers, whole numbers, counting numbers, any kind of terminating decimal or repeating decimal. Alright, so any fraction, any fraction that can be simplified. Alright, those are all the rational numbers. Then we have irrational numbers. Alright. Alright, and those would be like radical 2, non-terminating, non-repeating decimals that we don't know what comes next, pi. So these are irrational. Irrational. Alright, so that covers the real numbers. These are the real numbers. Okay. Real. And then that brings us to this. The imaginary numbers. If those numbers are real, these numbers are imaginary. They're not really imaginary because they exist. They exist and we call them imaginary because they're not part of the real number system. Alright, and imaginary numbers are often called complex numbers. Alright. So this is a totally different branch of numbers. These numbers cannot be found on a number line. And that's because all of these numbers fill the number line. Alright? And complex numbers take up this form. A plus bi, meaning the sum of the real parts of it, the real parts of a complex number and the imaginary parts. Alright, so this is an imaginary, any number that has a negative radical is an imaginary number. Alright, so let's talk about them a little bit. So 3 plus 5i is a complex number. Alright, so that would be a complex number. That comes up when solving quadratics, again, that don't have roots. But we can operate on them the same way we'd operate our regular numbers. So if we had 3i plus 5i, that's equal to 8i. Or 3i minus 6i is equal to negative 3i. Okay, so that still works. If we had 5 plus 2i, which is again a complex number, and we were to subtract 6 plus 3i, we will get 5 minus 6, which is negative 1, and 2i minus 3i, which is negative I. Alright, so it kind of works like a variable. It's just we actually do know what the value of I is. I is equal to the square root of negative 1. So that means that I squared is equal to negative radical 1 times negative radical 1, which is equal to negative 1. So that has implications when it comes to multiplying complex numbers. For instance, if we multiply 3i times 4i, that should be equal to negative 12. And the reason for that is 12 times the square root of negative 1 squared, or I squared, and I squared is negative 1, so 12 times negative 1 is negative 12. Alright? I to the third power is equal to negative I. And the reason for that is that's I squared times I. Alright? And that's I, so this is negative 1 times I is negative I. Here, so just to make sure that's clear, that's negative 1 times I, which is equal to negative I, or negative radical negative 1. Alright, we almost always refer to it as I when we can. I to the fourth is equal to I squared times I squared, which is equal to negative 1 times negative 1, which is equal to 1. And then this cycle repeats itself. I to the fifth is equal to I to the fourth times I, which is equal to I. So I to the sixth should be equal to I to the fourth times I to the second. So that's 1 times negative 1, which is negative 1. And this repeats. So I to the seventh is equal to I to the fourth times I to the third, which, if we saw before, was 1 times negative I, which is negative I. I to the 8th is equal to I to the 4th times I to the 4th, which is equal to 1. So the pattern should be that if I is a multiple of 1, is a multiple of 4, so 4 times something, it's going to be equal to 1. If it's a multiple of 4 with an extra I, it's going to be equal to I, like 5 and 1, first power. If it has a 2 extras, it will be equal to negative I. I'm sorry, it'll be equal to negative 1. If it has 3 extras, it will be equal to 1. No, negative I. Sorry. Because these would all become 1, leaving it being I to the 3rd, or I to the negative I. I'm sorry, negative I. Okay? So that's the I cycle. It goes radical, negative radical 1, negative 1, negative I, 1. I, negative radical 1. I'm sorry, I keep saying this poorly. It's going to be which is I. So we have I, negative 1, negative I, 1. I, negative 1, negative I, 1. Alright, and if you forget, you can remember that I is negative radical 1, and you can expand it and check yourself. Alright, so multiplying imaginary numbers. Let's take a look at that. It's possible you'll be asked to multiply 3 plus 4, 5i times 6 minus 3i. Okay, now this actually simplifies to a number, I believe. So 3 times 6 is 18. 3 times negative 3i is negative 9i. 5i times 6 is positive 30i. And 5i times negative 3i is negative 15i squared. So that's 18 minus, plus 21i minus 15i squared. So that's 18 plus 21i minus 15. And we said I squared is equal to negative 1. And again, the reason for that is that's the square root of negative 1 times the square root of negative 1 is equal to negative 1. So we get 15 plus 21i minus 15 is positive 15. And we get this is equal to 30 plus 21i. Alright. So you can multiply them as normal, it's just you have to make use of the exponents for I. Alright. And if we were given something else, let's say we're given I in a denominator, let's say we're given 3 over 5i, and we want to rationalize this denominator, because remember, I is an imaginary number, so it's also a radical, so it's a number we'd want to get out of the radical. We'll multiply it by the numerator and denominator by I, and we'll get 3i over 5i squared. Now you'd be tempted to simplify here, but we know that we can simplify that. So that's 3i over negative 5, because I squared is negative 1. And that would be simplified. Right. So one last thing would be to look at when we have a binomial denominator. And just like with radicals in our denominator, we want to rationalize this. So we're going to multiply by the conjugate, which is 3 minus I. So the numerator will become 9 minus 3i, and the denominator will be 9 minus 3i plus 3i minus I squared, which will simplify to be 9 minus 3i over 9 minus I squared, which is negative 1. So that's 9 minus 3i over 10. Alright, so because they work like radicals, they simplify similarly.